Hey everybody, this is Dr. Michael Timms. This is the second lecture on solubility. And we're going to just jump right in. And we're going to focus on coffee for a number of reasons. We're very familiar with it. We're going to have a lab focused on coffee. And this is an opportunity for us to look at organoleptic analysis or sensory analysis versus more typical analytical approaches using gas chromatography. But let's get into the coffee as a plant first. And there are two species out there that are in trade, Coffea arabica and Canephora, what is referred to as robusta. The fact that the arabica is considered the higher end coffee, and I think it's important too in that paper, if you review the growing conditions that they described, that arabica requires a lot more refined growing conditions, and in some ways that reflects to an extent what we should be aware of when we look at the growth of medicinal plants. And the article, one of the articles that we looked at was really looking at quality assurance. We'll have a couple of coffee readings, and that had to do with detecting superior beans. They used UV fluorescence for mold and infrared to look at cell wall thickness. I thought that was really interesting because it had to do with the appropriate cell wall thickness, allowing the bean to be literally cooked in its own roasting and the waters in it. And the processing, they went to processing almost immediately, sun drying, washing, and then dehulling. This is not too different from some of the things we do with a variety of plant flowers or leaves or even roots. Now the roasting part is that they looked at aromatic precursors, meaning those compounds that were present before roasting, and there were about 250 of those molecules. And the heat converted the water in the bean to a form of a pressurized steam. And that's where the hull thickness came in. And roasting techniques lasted anywhere from 90 seconds to 40 minutes. And it catalyzed a series of chemical reactions so that once the roasting was complete, you had more than 3 times the number of molecules that were present to give it its signature flavor, both in the mouth and in the nose. And some of the aromatics, when it came to the sensory descriptions, you can see huge numbers of ranges now, whether one person could detect all of these flavors at once. Maybe someone like a Robert Parker, who's known for his amazing tongue and nose in the wine industry. But it gives you an incredible range, everything from sweat to roses, cat scent, and Sauvignon Blanc. So you can see that the very presence of that variety in descriptive terminology really points to an underlying variety in molecular signatures as well. And so the important thing that they emphasize, and this is why they spent a little time with the mold issues, is only the strongest compounds are perceived, so that you can have different concentrations of some of these aromatics. But if you had a mold or something from a defective bean, the most powerful aroma would be something that wouldn't necessarily taste good or smell good. And so quality control for this type of product is really important. Now, if we could take that same training, lexicon of descriptors, and the ability to detect everything from adulterants to molds to the kinds of constituent profiles we were interested in, it would be very interesting to see where we could go with organoleptic analysis. And we'll discuss that more in the program as a whole. Look for some opportunities to participate in something like this based on the discussion forum on the community site. And here's a flavor wheel. I thought this was kind of interesting because it looks at not just coffee, but a range of pungents, sweets, bitters, sours, and salties, and breaks them out into resins. This is all really from plants, and then links them to TCM and Ayurveda, breaks them out further into energetics, descriptions of warm, dry, cool, dries. And then you start to get into some of the organ-based systems, stimulating digestion, carminative, laxative, all those. And then finally, it breaks them out into individual plants and where some of these might be found. So I think this is an interesting wheel to study and to keep with you. So one of the papers actually looked at all kinds of different ways to extract. And I think this is important for us as a starting point, because there are a lot of ways to extract medicinal plants as well, and we need to again have a rationale for why we're doing it. Certainly in the coffee industry, it's based on taste, but that taste is based on the presence of certain chemical profiles. So most drip, you have water that's near boiling. It flows over a loose aggregation of a medium ground coffee. It's in a filter for no more than 4 to 6 minutes. When we start to discuss yield later on in the trimester, we'll see how all these different issues come into play and questions we have to ask ourselves, and some givens that we understand about certain compounds or plants or classes of compounds. But again, this is something, use the coffee as a start point to begin to think about extraction as a process. Now, what's really happening is that you're dissolving most of the soluble acids in caffeine via this form. Now, when we look at espresso, this is something that's been brewed very rapidly in percolating a small amount of pressurized, heated water through a very compressed cake, very, very finely ground. And they can even define it in terms of the number of beans, right, 50 to 55. And this is done in about 30 to 40 seconds. This dissolves less of the soluble acid and only 60 to 70% of the caffeine. But because of the heated, pressurized nature of that it's water almost in a gaseous form, that we actually extract a variety of other compounds not present in the drip. And so here are some of the characteristics. When we look at that image on the top right, you're seeing gas bubbles. Right? This would be a gas bubble present as a boiled water in gas form, and that there are oil droplets around it, that there's something about the surface tension and that nature of that surface that seems to attract these oil droplets. When we see a good espresso, it's topped by a velvety thick froth, what they call the crema. And these tiny gas bubbles actually encase very thin films, and it concentrates. The concentrated liquor itself contains soluble solids and aromatic substances that are dispersed in this very oily immersion. And it also has because of that, has a very different mouthfeel. If you think about really paying attention to a cup of coffee versus a cup of espresso, very different in the mouth. Even when you go to your Americanos, pay attention to how it feels in your mouth. And it is very different. So this is from that article, and I thought it was interesting because if we look at this graph on the bottom horizontal area of the graph, we're looking at extraction time. And then on the vertical axis, we're looking at the chemical concentration in parts per million. When we start at just 10 seconds of extraction, you can see the distribution of compounds. And then on the right-hand side, those compounds, color-coded, are also linked to aromas. And if we look at the very top one, the light purple, it's rancid. And about midway down, there's a darker purple, which is rancid. And then a little bit further down is a brownish colored line, which is sulfur. These would be things that, for the most part, we don't want in our coffee. And look at how they change. They all start about the same amount, which would be around 0.25 parts per billion. And two of them, the dark purple and the brown, don't increase too much, but just around 30 seconds of extraction, that top rancid one, the light purple, really takes off. So this is based on espresso, and that's why any of you that have had these home espresso machines that don't really work as well as the nice machines that you see in a Starbucks or a good coffee house, they get run longer in order to increase the amount of espresso that gets pulled out of it. And we never have the same espresso that we can have in a good shop. And this is one of the reasons why. Also, if we look at the chemical composition of a raw versus a roasted Arabica, look at what happens. Not only is the water content really dropped, right now we're looking at the roasting, that chemical reaction, the catalytic process that happens in a bean that has the right shell hull thickness. And what do you see being changed? If you just look at the color coding, there are, I would say, two big areas that change and a third one that does change but not as much. So the most obvious one is the dark red. Right? These sugars, mostly polysaccharides, are reduced in the roasting. And then we look at the pink, which doesn't appear in the green bean. This is the caramelization or condensation products. And by condensation, we're not just talking about condensation on a window, but there's a class of reactions called condensation reactions, which tends to mean combining various chemical moieties or shapes into something that's different. It's a form of polymerization, but it's not really the same compounds being linked together, so it's not a polymer, but it is a form of aggregating different chemicals into a new shape, new form. And that's the heat acting largely on those sugars. The other area that is different is that dark brown, which are the acids, and you can see that they are actually reduced. And so there's a flavor profile in that roasting that a good roaster will know how long, be able to smell. There was, I don't know if it's still as good a place, but there used to be a great place in Old Town Alexandria. I had my health food store there. Misha's, which was right up the street. When he first started out, we were already in business, and he used to come down and buy product from us. And I used to hang with him when he was first starting out because he allowed us to smoke cigars in there. And I was not only at the store, but I was working on my doctorate, and I would do my writing in there with the smell of coffee beans roasting, smoking a cigar, and trying to finish the dissertation. And what was neat, though, is if you got to sit in there when he first started roasting, how the aromas would change in that. He had one big back room where the roasting took place, and how that would alter over time. And I'm curious whether the cigar smoke, most people back there were smoking cigars, whether the cigar smoke actually got infused into the bean. That would have been an interesting experience. But it does show you, here's an industry that has really done a lot to measure the changes of chemical profiles because they can associate quality on a sensorial level with those chemical profiles. And this is an area I think that the herbal industry could do a lot more to develop. So this is one of the papers that you've read, a comparison of 9 common coffee extraction methods, instrumental and sensory analysis. And this is the variety of different methods, and I think what's important here is to look at the temperature, right? They're generally all around the same except for one. The milling degree, we're going to come back to a number of these issues. So how much it was milled, how fine the grind is, the ground coffee per extraction. So this will come into play when you do extractions. There's going to be a maximal ground or powdered plant material to extraction solution in almost every case. And those are one of the things that we want to maximize, we want to rationally decide on. The volume of extract per cup, extraction time, and then pressures. So these are all sort of pieces of data that can then be linked back to what gets produced. So what they were trying to do is they were looking at how to correlate analytical evaluations with the sensory evaluations. And this is the way it broke out, was that total solids from the analytical evaluation was linked with texture and body on the sensory side. Headspace intensity, which is a terminology that they use in gas spectrophotometry, was associated with aromatic intensity. Concentration of caffeine and chlorogenic acids, specific compounds, were strongly associated with bitterness and astringency on mouth level. So when they did a plot, this was using principal component analysis, and I'll come back to this in a little bit more detail in a lecture later on in the trimester, without getting into too much of the statistics. It's just a very good way of looking for underlying patterns. And when you look at the sensory data on the left and the chemical data on the right, and they were two different principal component analysis plots, PC1 and PC2. And you have in A, there's about 70% of the total variance associated is accounted for, and 96% on the right of the chemical data. What it means is that the variability of there's less variability in the measurements in the chemical data, analytical data versus sensory. You would expect that to some degree, because you're looking at human fallibility, you're looking at a panel of professional trained testers, but it's still looking at biological variability, where on an analytical approach you're looking at an instrument that can be validated, its measurement capacity can be validated, meaning that all the elements of measurement can be controlled and the variability accounted for. So that's not unexpected. But I think what is interesting is if we look carefully, you've got 3 levels of sensory data rankings. So if we go back, look at the groupings. If we look on the left-hand side, the A sensory data, and we're looking at the top right-hand square, where it has the A fruity, F acidity, AS acidity. That's one grouping. The next grouping below it is all those others, with the third being a single grouping in the bottom left-hand quadrant, F sweetness. So you can see how sensory data actually breaks into 3 levels of analysis, where in the chemical data, it really only shows 2 areas, pH, fatty acids, and then all the rest are grouped together in the other quadrant. So these would be considered levels of rankings. And the idea that the sensory evaluation needs to be done by trained panels. So you have to ask yourself which method is better. Since we're looking at a product that relies a great deal on its sensory capacity, and certainly its ability to be pleasing in that respect, the sensory analysis seems to be a stronger and more accurate way to measure quality. So that's it. Thank you for your time.